All right, welcome to week 5. Let's get started. So now we're going to start with related rates. All right, we're actually going to be doing two things. We're going to be talking about related rates and maximum and minimum values. Shouldn't be too bad. Okay, so related rates. Now we're going to take what we've learned and we're actually going to start applying it to some pretty interesting physical phenomena. And we're going to start light and work our way up. So if you open up related rates, you're going to see this problem right here. Okay. If V is the volume of a cube with edge length x, we want to find the derivative of the volume with respect to time in terms of the derivative of the side length with respect to time. That's a pretty weird thing to say, right? What's really going on here, What's going on? So first of all, we've introduced there's actually 3 variables here. There's the volume, there's the length of the edge, and then there's time, okay? And we're letting the length of the edge of the cube change with time, okay? Which is going to affect the volume with respect to time as well. You might be wondering, what is this dv dt thing? Well, it turns out that derivatives have a lot of different notation. So far, we've just been doing y prime as a shorthand way of doing it. Traditionally, what we do is actually dy over dx, like that. The derivative of y with respect to x. And this is important because it tells you what you're taking the derivative of with respect to what letter. Okay, so when we start getting into more complicated formulas, such as the ones we're getting into today, it's very important to say the derivative with respect to what, sir? Okay, so that's what we're doing here, and we got to use this notation, dy dx, in order to make sense of all this. Okay, now, in order to make sense of this, we need to have a formula, okay? As the name of the homework suggests, we need to see the rate with volume and the rate with this the edge of the cube. How are these rates? Rates of change related? Okay. Well, we start with the basic formula, which is volume and edge length, which is this. Okay. It's a cube, so it's length times width times height. X times x times x. All the sides are the same length, so it's not a big deal. Now, just like what we did before, we are going to take the derivative with respect to time on both sides. And since we just did implicit differentiation, we're going to apply the exact same reasoning here. So on the left, we have dv, On the left, we have dv over dt. And over here, we have, we're going to take the derivative with respect to x. If you want, we can make this easy. We'll do it exactly the same as we did with implicit differentiation and keep, the primes. So this is v prime on the left, and this is 3x squared, and then x prime, okay? You might be thinking, wait. In implicit differentiation, we just left it as 3x squared. Why are we doing it now? Well, this time we're taking the derivative with respect to t, okay? And notice that there's no t in here at all. Okie dokie. Okie dokie. Now, they want this in a particular notation. So in order to do this right, we're going to do dv dt. We'll just replace all the v primes and the x primes with their correct thing. So 3x squared, and then we've got dx dt. That would be the correct answer, I think. And just to make sure that it's put in the right way, there we go. Yep. See, 3x squared. Yep. Okay, good. So I was just checking because I didn't know if I had to type in dv dt. All right, yeah, so 3x squared, and then dx dt, and we should be good, hopefully. Hopefully the check answer button works. Great. And that's the basic idea. All right, related rates. Area of a circle. So again, A is the area of a circle, R is the radius, and we got to find the derivative with respect to t again. We need to relate area with radius. Here, I hope you guys are good with this now. The area of a circle is pi r squared, just like that. Okay, take the derivative on both sides with respect to t, and you have an r prime right here, and that means we're going to have basically dA dt, and we've got 2 pi r, and then we've got dr dt. That would be the basic idea. Okay, so we're just doing implicit differentiation again. That's the idea. And then we start getting into some tougher ones, you know. Let's see. Let's get into a really good one. How about, here we go. Let's get into a nice word problem, like number 6. Okay. So, if a snowball melts so that its surface area decreases at a rate of 1 square centimeter per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. All right. So, this is a word problem. It's a lot like what you're going to see when you do your IB exams and whatnot. Well, how do we handle this guy? Well, we got to get a formula, okay? A snowball melts so that its surface area decreases at blah, blah, blah. Okay, so we got a few pieces of information. First of all, it's a snowball, which means it is a sphere, okay? And we need the surface area of a sphere. If you look it up, the surface area of a sphere should be, 4 pi r squared. Okay. Pretty sure that's right. Let me look it up just real fast. It's been a long time. Surface area of a sphere. Let's see. Yep, 4 pi r squared. Okay, good. My memory isn't quite what it used to be. Okay. A few other pieces of information they're giving us. The surface area is decreasing at a rate of 1. So that means that S prime is going to equal -1. All right? It's decreased. So the rate of change, S prime, is -1. And what we want to do is we want to find the rate at which the diameter, which is D, decreases. So we want to know what is the rate of change of the diameter when the diameter is equal to 10. Okay? That's what we want to know. We want to know the rate of change of the diameter when the diameter is 10. Okay, well, let's try to figure that out, shall we? So down over here, let's start with this. S equals 4 pi r. By the way, everything is in terms of r and the diameter and stuff. And I know that the diameter is actually 2 times r, okay? Which means that r is going to equal d over 2, right? So that means that when we have s is equal to 4 pi r squared, that's basically the same thing as saying s is equal to 4 pi d over 2 squared, okay? We need to make sure everything is in terms of the diameter, not in terms of the radius. And let's simplify this to make our lives a little easier. The square distributes to both of them, and we get s is equal to 4 times pi times d squared over 4, but the 4's cancel out, and s will equal pi d squared. Very nice. Now, just like before, we're going to do implicit differentiation. So we get s prime is equal to pi. Pi is a constant, so it's not a weird variable or anything. 2d and then d prime. Okay, sounds good. Let's see. Well, let's plug in what we know, right? So s prime was equal to -1. So we'll do that. We got pi, we've got 2. D was equal to 10. Very cool. And d prime is the one we're trying to look for. Okay? So that means with a little bit of algebra, we should get d prime is equal to -1 over 20 times pi. That guy right there. You might be thinking, holy crap, what have I gotten myself into? Actually, it's not that bad. If you got implicit differentiation down, this is just like a couple extra steps, you know? So once you've got implicit differentiation down, this is just a little bit more. So one more time from the beginning, you got to realize a snowball is a sphere, and we're looking for the surface area of a sphere. You look it up, surface area of a sphere is 4 pi r squared. S prime is equal to -1. We're trying to find d prime, and they're telling me the diameter is equal to 10. Well, the original formula was in terms of the radius, so I need to relate the radius to the diameter, the diameter is equal to 2 times r. So that means the radius is half of the diameter. We substitute that in there. Great, stuff cancels out. We do implicit differentiation. We plug in the values that they gave us and we solve for d prime. And then we got it. So hopefully the check answer button helps. Well, that would be the right answer, right? Yeah. Okay, let's do one more, I guess. How about... Here, how about number 9, and then we'll go on to max min. Okay. A plane is flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour and passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. Okay. Okay. So what we need right here is we need a diagram. You know, we need to see what's going on here. So let's draw this out. Okay. The plane is like, let's say this is the radio station, R. And let's say the plane kind of starts right here, you know. We'll say that this is the starting spot. We'll say S. Okay. And we'll have some, it's flying horizontally. We'll call this like X, I guess. We'll call this like the final position right here. Okay. And this is bad because I'm doing this with a mouse, but what are you going to do? Okay. It has an altitude of 1 mile. So we're just going to say, all right, that's 1 right there. Let me pause this. Back at it. Sorry, that was my phone. Okay, we also need one more thing. Let's talk about, you know, let's say the distance of the plane to the radio station. We'll call that D right here. Okay. Okay. Now let's get some information here. Okay. The altitude's 1. And a speed of 500 miles per hour. All right, so that means that the speed, which is the change in x over time, so that means x prime will equal 500. And it's positive 500 because it's moving away from the radio station. So x is basically getting bigger, so we know it's positive 500. Okay, find the rate at which the distance from the plane to the station is increasing. So we want to know what d prime is. When it is 2 miles away from the station, that would mean D is equal to 2. Okay? Okay. Now, it looks like we're going to have to do a little bit of figuring out stuff in order to get to the end here, but we'll figure it out. Okay. So, we need a way to relate all of these together. How do we do that? Well, it's pretty simple. This is a right triangle, and we have 3 sides of a right triangle. Never mind the fact that 2 of the sides are getting bigger, it's still a right triangle. And the way we relate 3 sides of a right triangle is with the Pythagorean theorem. A squared plus b squared equals c squared. Okay, let's fill it in. We've got 1 squared plus x squared equals d squared. Very cool. All right, doesn't seem too bad. We should probably take the derivative, right? So let's do it. This is going to be 2x x prime and 2d d prime. The 2's will cancel out on both sides, so we get x prime is equal to d prime. All right, now we're tempted to just fill in our values, right? So we don't know what x is, so we'll leave it there for now. This one's 500, okay? D is equal to 2, and we're looking for d prime. Uh-oh, what are we going to do here? We've got, everything looks fine except we don't know what x is. How do we do this? Well, let's hold on a second here. We can go back to one thing. What about, we need to find out what x is. Well, we know that d is equal to 2, so when we look at the second line here, 1 squared plus x squared equals d squared, we should be able to solve for x now, you know? So we start with this, 1 squared plus x squared is equal to d squared. We know that d is equal to 2. So 1 plus x squared is equal to 2 squared. Okay, this is looking nice. So x squared is going to equal 4 minus 1 is 3. So x should equal the square root of 3. And we know when we take a square root it's plus or minus, but distances are always positive. So we know that x is going to equal square root of 3, which means when we come back to our formula, 500, come on now, 500 is equal to 2d prime, we can now plug in the square root of 3 right in for x times 500 is equal to 2 times d prime. And that means that d prime should equal the square root of 3 times 250, because you divide both sides by 2. And that would be about how fast the plane is going away from the radio station when the distance is equal to 2. Notice that this related rates problem is a little bit more difficult than the ones before, because you got to do some fancy substitutions and whatnot. And we got to find a really creative way to get around things. So we start by saying, okay, the speed is 500 miles per hour, and it's horizontal. First of all, the tough part is we don't have a diagram, So you got to make a diagram first. Then you got to get your values. You need to find a way to relate all 3 sides of this triangle using, pre-calculus and trigonometry. We would say a squared plus b squared equals c squared. Plug in our values, do implicit differentiation, and simplify, and we find out, we got everything fine, but we don't know what x is. So then we double back and we look at some of our formulas. Hey, d is equal to 2. Let's plug that in there and solve for x. Now we have x. We can plug it in, and d prime is now done. See what I mean? All right, and that's basically the idea of related rates. And all of these are going to involve something similar. You're going to need to make a diagram, and you're going to need to say, what is this diagram? Here's a cone, so you're going to have to look up a formula for a cone. All of these problems, 1 through 14, y'all should be able to do pretty well. It's gonna be tough, but you should be able to do it. All right. You can think of all these word problems as IB exam style questions. These are all very good IB exam style questions. And if you want really good practice for this sort of thing, these problems are definitely it. All right. All right. So that's related rates in a nutshell. Now, on to maximum and minimum. Okay. So maximum and minimum values. Okay, if you have a TI-84, this will actually feel pretty good. Okay. If I can, should I do this in GeoGebra? Yeah, I guess I could do this in GeoGebra. Let's see. GeoGebra calculator. Okay, if you have a graphing calculator, this will actually not feel too bad. So, when we're looking at maximum and minimum values, okay, like let's say we're looking at a physical situation and we're interested in knowing when something is maximized or minimized. Let's go with the classic example of supply and demand, okay? You're running a Wawa, all right? You're the manager, the general manager of a Wawa, and you have to decide how many sandwiches are you going to make and what price are you going to set them at, Well, let's suppose, you release a big announcement and you say, okay, for half an hour only, all sandwiches of any size are going to be $3. For 30 minutes on Wednesday from 4 to 4:30. What do you think is going to happen? Well, all the sandwiches are going to be gone, and you'll have made, this much money. Okay? You'll have sold all your sandwiches, but you probably didn't make as much money as you could have. And that money you need in order to pay your employees and pay the electric bill and all that other stuff. So did you make as much money as you could to pay all the bills and pay all the paychecks? Maybe not. So maybe that was too low of a price. Then the next Wednesday, you're like, all right, well, I'm not going to make that mistake again. I'm going to do the exact opposite. From 4 to 4:30, we're going to set the price of all sandwiches at $12, something absurd like that. $12. There might be some hungry people who will pay it because they can't, they got to have a Wawa or whatever, but not a lot of people are going to show up. So you're going to have that other problem, okay? You want that sweet spot where you want, or you're going to maximize the profit. You want the one where the profit is totally as high as possible, totally maximized. This is the idea of trying to find a maximum or a minimum, okay? So we've got two things we want to talk about: absolute maximums and local maximums. All right? Local maximums are the easy ones to understand. If you graph the function, which we're going to, and you get something that looks like this anywhere in the function, that right there is an absolute maximum. This right there is like is a local maximum, because the values just to the left and to the right of it are smaller. So that means it's local. And the same thing here. The values just to the left and to the right of this guy are bigger. So that means this is a local minimum. Okay? Absolute maximums and absolute minimums have a special definition. Okay? That's where it's the highest maximum possible. All right, it's the highest maximum possible, or the highest or the lowest minimum possible, given our domain. Okay, so given all of our maximums or whatever we have in our in our domain, we want to pick the point that is the highest point. Okay, if you get to it, some of you are thinking of majoring in math. You're going to take a class called Advanced Calculus, and you'll have this idea of a supremum and an infimum. The absolute maximum is called the supremum, and if you want to get really technical, that would be the limiting number that all numbers approach. All right, so all number, it's like the smallest possible number that's bigger than all the numbers in your domain. That's called the supremum. And the infimum is the biggest possible number that is smaller than all of the numbers inside your region. Okay? And the supremum and infimum might be infinity. It's possible. Okay? All right, no big deal. I think, as I recall, with number 1, they kind of expected you to graph this guy. Pretty sure they wanted you to graph it, because when you get to these guys, so when you get to number 2, that's when we start talking about getting more abstract. Okay, so for number 1, this should be pretty chill. You can actually even use GeoGebra, and I honestly don't care. So let's do that. 1 plus 2x. So I'm going to go over here and I'm going to say y is equal to 1 plus 2x. There should be a way to do a domain on this guy, right? X is less than or equal to 1. Could I do that? Yeah, I guess I can. All right. That kind of works. And then this weird guy's over here. Okay. So this is x is greater than or equal to negative 1. Okay. So this is greater than or equal to negative 1. Cool. So ignore this horizontal line. All right. What is the absolute maximum? Well, it's infinity, right? It is infinity. I don't know what I did for local maximums. Let me just check really fast. Oh, and NA if they don't have a value. Okay. Okay. Sounds good. So that means if I'm looking at this guy, if there is no local maximum or minimum, use NA. Okay. So there, if you look at it, there is no local or absolute maximum here. Okay? A local maximum has to do this, has to be a curve, has to curve up and stuff. This one clearly doesn't. So there is no absolute maximum, and hell, there's no local maximum either. However, when you look at it, the minimum is pretty clear. We're looking at y values, by the way. The lowest possible number here is negative 1. And since there is only one possible local minimum. The absolute minimum would be the smallest of all the minimums, which should be -1. Very cool. Let's do one that's a little bit cooler here. How about 1 minus x squared? All right, let's check it out. 1 minus x squared, and it's 0 is less than x is less than 1. Let's try that. Did I do that right? Yes. Okay, so let's zoom in on this guy. We're only looking at this guy right here. Okay, so we're just inside this square in the first quadrant. All right, we're not looking at anything else. Okay, ignore these horizontal lines. In fact, I wonder if I could do this. Would GeoGebra let me do this? Oh, okay, good. So I got to put in parentheses. All right, that makes sense. Okay, what's the local maximum? Well, there's only one maximum here, and that would be the 1. So I would have to say 1. That's the only maximum that I see, only local maximum. And the absolute maximum would have to be that one, right? Because it's the biggest one in that whole region. Likewise, looking at this guy, the absolute minimum and local minimum are all the same. It should be 0, 0, right? Should be. So 0, 0. Pretty sure that's right. Ooh, I'm wrong. Oh, what did I do wrong? I typed it in right. 1, 0, 1, 0. Why didn't it like it? Okay, boss. Why don't you like it? Did I type it in the wrong thing? 1, 0. Did I type it in the wrong guy? Maybe I typed it in the wrong guy. I must have typed it up here by accident. Yeah, it's this guy. Okay, so number 1, you really just graphing and looking. It's not a big deal. Where it gets interesting is when we start talking about number 2. Okay, because you got to find these guys analytically. You want to find the critical numbers. Okay, critical numbers. This is what you do when you need to analytically find maximums and minimums. Okay, so let's say we got like a random function that looks like this, a random continuous function, kind of doing something like this, like that. All right. Critical numbers are these guys. Boom, 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 boom. Okay? These are called critical numbers. When I was in college, we also called them stationary points. Right? All right. How would we find these stationary points? Well, they all have something in common. All right? What's that thing that they have in common, you might ask? Well, I'll tell you. All of them have this in common. Okay? If you were to ask me what is the slope at that point, the slope is always going to equal 0. Okay? So the critical point is when you have like dy, basically y prime. Y prime will equal 0. All right? The slope is always going to equal 0. So what x values give you a derivative of 0? Those are called critical numbers, aka stationary points. All right? So if I'm looking at like 2a, all right, what I would do is I'd say, okay, well, I've got basically y is equal to 2x minus 3x squared. And if I want to find all the critical points, I have to take the derivative, which is 2 minus 6x, and I have to set it equal to 0. And I got to solve for x. With a little bit of quick algebra, you're going to find that x is going to equal basically 1 over 3. Okay? That would be the only critical number for this first guy. See? So the only critical number for this first guy is 1 over 3. Check answer button failed, but that is how you would do that. Okay? Same thing here. 5 plus 8x. You take the derivative. That means y prime is going to equal 8. All right? And you set that equal to 0. Notice that there is no x value that's going to make 8 equal 0, so you're going to say NA. There are no critical numbers here. And that makes sense because 5 plus 8x is a straight line. It's not going to have that curvy feature. In fact, if I graph this first guy, 2x minus 3x squared, what are we going to get? 2x minus 3x squared. What are we going to get? There, right at about 1/3 is our critical value, right there. Okay, but if I type in that other guy, 2 minus 8x, that's a straight line. We're not going to get that curvy thing. It's not going to happen. You know? And so on and so forth. So like, let's say, I don't know, let's say we've got something really funky. How about, what's a good one? How about we do a tough one? Sine squared of 2 theta is equal, is equal to 0. Okay, let's try that one. Okay, so I'm going to start with this. Y is equal to sine squared of 2 theta. All right, there's 2 ways to do this. You can do the chain rule, which is what I recommend. You can also use a formula, which is also pretty cool. I like the chain rule myself. So y prime, that's going to be derivative of the outside, so 2 sine of 2 theta, times the derivative of the inside, which is cosine of 2 theta, and then the derivative of the inside, which is just 2. And we got to know, when does this equal 0? Okay, take the derivative of, well, maybe we can divide both sides by 4, basically, and you're going to say sine of 2 theta, whoa, cosine of 2 theta is equal to 0. Okay, this can only equal 0 in one of 2 ways. Either the sine of 2 theta equals 0, or the cosine of 2 theta equals 0. Okay? We've got either of these 2 situations. Let's start with the first one. When is the sine of 2 theta equal to 0? Well, we use our formulas. This is 2 sine of theta. We'll do parentheses here. Cosine of theta equals 0. Well, this only happens when cosine equals theta, or sine of theta equals 0, or cosine of theta equals 0, right? Well, that means that, if you remember the unit circle, this happens when, okay, we got 0 or pi, okay, for sine. And for cosine, it's pi over 2 and 3 pi over 2. Okay, cool. So that's our first set of answers. And then we do it again for cosine of theta. So let's go down over here. Okay. So when is cosine of 2 theta equal to 0? Okay, well, we can use a nice formula. I like the idea of, let's do this one. Cosine squared of theta minus 1. Okay. Oh, it's 2. Sorry. 2 cosine squared of theta minus 1 equals 0. Okay, let's solve. So cosine squared of theta is equal to 1/2. We square root both sides, so cosine of theta is equal to basically plus or minus the square root of 2 over 2. All right, and this happens only, again, use the unit circle. Very important that you have your unit circle totally on lock for these guys. This only happens when you got pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay. All 8 of these answers would be critical numbers here. All right, they're all between 0 and 2 pi. So one more time, what do? Well, you got this guy, you got to take the derivative, set it equal to 0, and solve. And for this one in particular, you got to be really good about knowing what is what. Okay, the derivative sine of 2 theta. Use a formula, totally fine. And you got to use your unit circle to get your critical values, and then you're done. I like it. That's super cool.
So it snows.
I love it. Okay, I'm almost done here. And that's that. Okay, so kind of hard. But that would be the basic idea behind maximum and minimum values. And same deal here. Now, what do you want to do if you want to find the absolute maximum, absolute minimum without using graphing? Okay? Without using graphing at all. Okay, what you would do is you would take the critical numbers. So let's say we're looking at 3a, and then we'll call it quits for the day. Let's say we're looking at this one. Y is equal to x squared minus 2x plus 2. We got to take the derivative, so 2x minus 2 set it equal to 0, which means that x is going to equal 1. Okay, and that's within our domain, 0 to 3. Okay, it's because 1 is between 0 and 3, so that's good. What we want to do to get our absolute maximum is we want to take the value of 1 and plug it in order to find our value. Okay, so we've got x squared minus 2x plus 2. Let's put in a 1. So we got 1 squared minus 2 times 1 plus 2. This is going to equal 1 minus 2 is negative 1 plus 2 is 1. So this is our y value. Now the next question is, how do we know if it's an absolute maximum or an absolute minimum? Is it a maximum or a minimum? How do we know? Okay, well, one more thing we need to know, which is called the double derivative. Again, this is why we have higher derivatives. We want to know what the double derivative is. Okay, so y double prime. Well, in this case, the y double prime is 2. All right. Y double prime is equal to 2. That means that the y value is always like we're always kind of sloping upward, if you will. All right, we're always trying to change direction upward. Why does this meaningful? Well, if y double prime is positive, we've got a minimum. All right. If y double prime is negative, we've got a maximum. All right, and it's kind of hard to describe without my hands, but if it's positive, you want to think like the rocket boosters are going up, which means that if there is a critical value, we're kind of trying to change direction. We're trying to get away from the ground. We're blasting off from the ground and accelerating upward. That's going to create a minimum. And same thing with maximum. Let's say something's trying to suck us up into the air and we need to get away from that. We need downward acceleration. We're going to actually trace out the path of a maximum in that case. And since y double prime here is always positive, we know that this y value of 1 is going to be a minimum because y double prime is positive. All right, that was a big mouthful, so maybe we want to do one more. How about let's try x cubed minus 12x plus 1. Okay, so y prime is equal to 3x squared minus 12. We want to set that equal to 0 to get our critical value. So plus 12 divided by 3, x squared is equal to 4. So that means x is equal to plus or minus 4. Okay, plus or minus 2, I mean. Plus or minus 2. And we look in here. Let me back up here. That's how we get the local maximum and minimums, but we also have to plug in 0. All right, I got to go backwards. But let me back up to 3a, okay? Because I didn't realize this. This is how we find local maximum and minimums. The 1 here is a local minimum. All right, this is a local minimum. But how do we know if this is the absolute minimum or what's an absolute maximum? Well, what we also need to do is we need to also plug in the endpoints, 0 and 3. Okay, we also need to plug in 0 and 3 in order to finish this guy off. So kind of wrong of me to jumped the gun there. So what happens if I plug in 0 here? Well, if I plug in 0 into the original function, 0 squared minus 2 times 0 plus 2, that's going to equal 2. So this looks like a maximum or something. Let's plug in the other one. So 3 squared minus 2 times 3 plus 2. So this is 9 minus 6, which is 3, plus 2, which is a 5. This looks like some kind of maximum too. All right, so the absolute maximum looks to be 5, and the absolute minimum, the smallest number, looks to be a 1. And that would be the correct answer. Okay? So absolute maximum is 5, absolute minimum is 1. Check answer button, of course, fails. Okay? All right, so I forgot to include the endpoints there because we're talking about absolute maximums and minimums, not locals. Very cool.
And
Oh, that's cute.
it's baby pig.
Very cool. All right, I'm almost done. Hang on.
Okay.
Okay, let's do one more and then we'll call it a day. All right, let's check out this one. Y is equal to x cubed minus 12x plus 1. Okay, y prime is going to equal 3x squared minus 12 is equal to 0. X squared is equal to plus or minus 4, which means that, 4, and that means that x is going to equal plus or minus 2. That's well within our domain. We need to plug in these critical values to see if they're going to be candidates for maximums and minimums. So let's do that now. Y is equal to negative 2 cubed minus 12 times negative 2 plus 1. That's going to be negative 8 plus 24 plus 1, which is 25 minus 8, which is 17. So this is what happens when you plug in negative 2. What happens if you plug in positive 2? All right, well, this is 2 cubed minus 12 times 2 plus 1. This will be 8 minus 24 plus 1. That's going to be negative 16, negative 15. So this looks like a nice minimum possibly. But we also need to include the endpoints, negative 3 and positive 5. So let's see what happens. All right, negative 3 cubed minus 12 times negative 3 plus 1. Let's see, 9 times 3 is negative 27. This one's plus 36 plus 1. So that's going to be 9 plus 1, which is 10. That doesn't look like that. That's not going to beat 17 or negative 15. And then let's do the last one, which is 5. So 5 cubed minus 12 times 5 plus 1. Okay, 25. This is 125. All right, minus 12 times 5, which is 60, plus 1. This already feels pretty good. 40, 65, 66. So these are our 4 numbers, okay? The first 2 are local maximums and minimums, definitely. But then we also need to find out like the other critical value, the other values we need to think about within our domain, and that means we need to include the endpoints. And when you look, the smallest number seems to be negative 15, and the biggest number looks to be 66. So the absolute minimum here is negative 15, and the absolute maximum is 66. And that would be the basic idea behind all of these guys. Okay, we'll talk about this tomorrow. We'll see how you guys do. Anyway, take care and have a good day. Bye-bye.